Okay, let's begin lecture number 8. So in lecture 7, we have learned about semi-crystalline polymers and their behavior in terms of melting and crystallization. Okay. So semi-crystalline materials have melting point and crystallization point. And also, we have learned that semi-crystalline polymers are not 100% crystalline. So they also exhibit glass transition temperature. Here in lecture 8, we'll learn more about amorphous polymers which have glass transition temperatures. So if you see the amorphous polymers, at high temperatures, amorphous polymers are basically liquid. On the other hand, below glass transition temperature, denoted as Tg, they are frozen liquid. They are considered as frozen liquid. So basically, overall chemical structures are similar. At high temperatures, they are just random molecular structures, polymer chains. On the other hand, at low temperature below Tg, overall the amorphous structures maintain while their movement are frozen. So we want to see exactly at what kind of molecular behavior, molecular movement are related to these glass transition temperatures. We'll get back to this point later. Okay. So as I just mentioned, amorphous polymers have glass transition temperatures. You might recall from a basic experiment when you did the DSC measurement. When you measure DSC of polymer, you could check its glass transition temperature. On the other hand, as I just mentioned before, semi-crystalline polymers are not 100% crystalline. Some parts are crystalline and some other parts are amorphous. So crystalline parts have crystallization and melting temperatures, while amorphous region have glass transition temperatures. And if you compare the melting and glass transition temperatures, generally many of the polymers, the glass transition temperature is between like 0.5 and 0.8 of the melting temperatures in absolute temperature scale, about like 2/3 of the melting temperatures. So up to here, we learned that amorphous polymers have glass transition temperatures. So we have the first question. Why do we need to really care about glass transition temperatures of amorphous polymers or other semi-crystalline polymers whatsoever? The reason why is very simple. Glass transition temperature basically determines the use temperatures for many of the polymers. For example, let's see two representative examples of polyvinyl chloride, PVC, and rubber. PVC is an example of thermoplastic, and there are many different kinds of PVC, including Tygon tube, leather, or pipe. All these three are PVC, amorphous polymer. And as you add more plasticizer, for example, phthalate, so we'll learn about more in details about plasticizer later. So as you add more plasticizer into the PVC matrix, the glass transition temperature of the resulting PVC changes, especially decreases as you add more plasticizer, and the properties, physical or thermal properties of PVC changes significantly. For example, if the content of plasticizer is very small, the PVC is basically used as pipe, very strong, hard materials. On the other hand, if you had a little bit of plasticizer, it becomes like leathery. It becomes like leathery, like a leather we put on. For example, this leathery PVC is used for oral cover seat in the car. If you add more plasticizer, it becomes the Tygon tube that we usually use in our experimental lab. So although all these three are same PVC, only difference is the amount of plasticizer in it. Their properties are quite different. Similarly, if you look at the rubber, an example of the thermoset, so as you have learned before, rubber is lightly cross-linked polymers. And as you increase the degree of cross-linking, for example, polyisoprene is very flexible rubber. On the other hand, if you do more cross-linking, for example, PDMS is much harder than polyisoprene, and more cross-linked polymers, which is called ebonite, is really hard rubber. So by changing the degree of cross-linking, we could change the glaciation temperature and also the resulting the physical properties of the rubber. So if you look at the comparison between like high TG or low TG polymers, for example, PMMA, and if you compare PMMA with PDMS, PMMA has relatively high TG. As I recall, PMMA's TG is around like 100 degrees C, at least over 80 degrees C. And at room temperature, which is much lower than PMMA's TG, this PMMA basically exist as hard or rigid and glassy material. An example of PMMA is plexiglass, very hard plastic. On the other hand, for PDMS's TG is much lower than room temperature. And at room temperature, PDMS is basically very flexible rubber. So depending on the TG of the amorphous polymers, their physical states are quite different. Okay. And another interesting feature of glaciation is it is dependent upon the kinetic behavior. Especially the external stress or timescale, the rate of experiment, also affect the glaciation temperature. So it's not really easy to understand what this means, right? So let's see an example for silly putty. So silly putty is kind of a clay. You might have experience playing with it when you were a child. In Korean, silly putty is something like 고무차르. So you might recall playing with this silly putty before. So if you recall the physical behavior of silly putty, if you slowly increase the length of this silly putty, you can experience that it slowly expand. I cannot say expand. It slowly stretches to a longer length, right? So it means that it behaves something like a very flexible material. On the other hand, if you abruptly break this silly putty, it just breaks out, right? So if you change the time scale, if you slowly stretch this silly putty, it behaves something like a rubber or flexible material. But if you change the time scale, if you abruptly, if you decrease the time scale significantly, if you increase the rate of experiment significantly, then the slippery behaves like a solid material. So although we are using the same material, exactly same material, depending on the time scale, rate of experiment, especially the kinetics, it changes the glass transition temperature. It's very interesting behavior. That's why people don't really understand the exact mechanism of glass transition even after studying about this for like tens of years. Alright, so let's learn a little bit more in detail about glass transition. First, let's consider this glass transition in terms of thermodynamics. If you recall from physical chemistry or thermodynamics class, small molecules have first order or second order phase transition. You might recall this, right? From the chapter 4 of the Atkins physical chemistry book, right? So you pretty much we have learned about first order phase transition, including like melting and boiling. Remember, right? For example, if you plot the volume as a function of temperatures, at the melting point, volume changes, right? Volume abruptly increases, right? And at the boiling point, it also abruptly increases the volume of the specific material, right? And when we have learned about this, the phase transition, we define the first order phase transition as the first derivative of the chemical potential is basically this shows the discontinuous behavior such as volume, entropy, or enthalpy, right? Remember? On the other hand, we learned that second order phase transition, the definition of second order phase transition is something at which like the first derivative of chemical potential is continuous, but the second derivative of the chemical potential is discontinuous, right? The reason why I'm explaining this again is because glass transition is a kind of second order phase transition. So, for example, if you plot volume, specific volume is the volume per mass, specific volume as a function of temperature, for example, for amorphous polymer, at Tg, the volume does not show any discontinuous behavior. It is continuous, right? Only the slope changes, right? That's the definition of second order phase transition that we have learned before, right? Interesting, right? So glass transition is kind of second order phase transition. Similarly, if you check the specific volume as a function of temperature for semi-crystalline polymers, we have learned that semi-crystalline polymers have Tg as well as Tm, right? So it has Tg here, and also Tm, melting temperatures, at which the volume abruptly increases. This shows this continuous behavior. Another interesting behavior that we have just learned here, in which the glass transition depends on the time scale or rate of experiment, can be observed by doing experiment. Let's say that we have amorphous polymers at high temperature here, high temperature here. If you cool this sample like this, like this, okay, at glass transition temperature, it will show different like slope, right? But let's assume that you cool at relatively fast rate. If you cool it at a relatively fast rate, what happens is that it just froze at a relatively higher temperature here, right? Yeah. So At slow cooling, the TG was here, right? But at fast cooling, TG is here. TG is increased. Although we are basically measuring the same material, by changing the cooling rate, this time scale or rate of experiment, the measured TG is different. It's very interesting behavior. Right? So what exactly like this TG is related, what kind of molecular motions inside of polymer chains are related to this glass transition? So in terms of molecular motion, there are many different kinds of molecular motions in polymers. So here, 4 different kinds of molecular motions are described. So A, the vibration of atoms about equilibrium position. It's very small motion, right? The vibration of each of the covalent bond. Right? A little bit larger in a little bit larger scale. B, motion of a few 5 to 6 atoms along the chain or of the side group. Some a little bit larger motion compared to the vibration of the chemical bond. And C, cooperative wiggling and jumping of approximately 40 to 50 carbons. This is a little bit larger molecular motions of the polymer chains. And D is the translational motion of the entire molecules. So entire polymer chain could move, right? And for the last tens of years, people have found out that glass transition is related to this molecular motion, like cooperative molecular chain motions of like tens of polymer chains. Okay? Which means that below TG, there is basically little or no cooperative segmental polymer chain motions on time scale of observation. On the other hand, above TG, there are cooperative segmental motions, tens of, even up to a few hundreds of segmental motions. Okay? So TG is the temperature at which these kind of cooperative polymer segmental motions exist or don't exist. Okay? That's the boundary. Okay? Very interesting behavior. So as we already have learned, TG is kinetic behavior. So in other words, it's viscoelastic phenomenon. So we'll learn about this viscoelastic behavior of TG in more detail later. So as I explained here, fast cooling, also time scale experiment, TG depends on the experimental rate. So if you do the experiment at slow rate or long time, it lowers TG, okay, which means that it behaves like a flexible material. On the other hand, if you increase the experimental rate or if you do the experiment at shorter time, then you remember silly putty behaves like solid, right? Which means that its TG is higher. Okay, so TG is very weird and very interesting experimental behavior, like the behavior of the amorphous polymers have. All right. So this class, since we have covered the contents about the semi-crystalline polymers, their thermal behavior, remember, like semi-crystalline polymer. So at high temperature, it is basically viscous liquid, or we call it melt. Okay, below a certain temperature, which is called crystallization temperature, it becomes crystal. Okay, and above the melting temperature, it becomes viscous liquid. Okay, How about amorphous polymer? If you recall, amorphous polymer at high temperature similarly melt. But below a certain temperature, which is called TG or glass transition temperature, it becomes similar structure but rather like a solid or like, let's say, frozen liquid. Okay, so basically frozen liquid and melt of the amorphous polymer is not really melt. Above TG, amorphous polymer becomes somewhat melt-like structure. Okay, but overall microstructural polymer chain structure is similar. Okay, but they experience thermal expansion. So basically they show volume change. Okay? So, for example, for amorphous polymer, if you plot volume, which is called specific volume of polymer, as a function of temperature, okay, at a certain temperature, volume shows a certain change, and that temperature is called glass transition temperature. Okay. The interesting thing about glass transition temperature is that it is viscoelastic phenomena. So we need to show that what polymer is. Okay. So we usually say that polymers exhibit viscoelastic behavior. Okay. So here, visco means viscosity. Viscosity, which is a property of liquid, right? Also, polymer exhibit elastic property. Elasticity is a property of solid. So polymers, interestingly, exhibit both liquid-like and solid-like characteristics. Okay? So the interesting thing about this viscoelastic property of polymer is that it depends on the experimental rate, or it is kinetically determined phenomena. For example, let's consider this specific volume change at glass transition temperature. Let's say that we start from here, okay, and we just cool down we decrease the temperature, okay. And in first case, let's say that the cooling rate is relatively slow, okay. Then it will follow this kind of behavior. Below glass transition temperature, it becomes like a frozen solid. But if the cooling rate is really large, then if you decrease the temperature abruptly, for example, it follows like this. But if the cooling rate is very fast, it suddenly becomes like solid. Okay, the polymer chains do not move. at all, right? So in that case, glass transition temperature is higher than slow experimental rate, slow cooling rate. Okay? So glass transition temperature itself depends on the experimental rate, okay, time scale. Okay? So this kind of transition, the glass transition temperature, for example, this kind of transition is called second order phase transition. You might recall the Ehrenfest classification of phase transition in physical chemistry class, right? Melting, evaporations were first order transition, right? On the other hand, this glass transition is second order transition. Okay? So, for amorphous polymer, the specific volume shows this kind of change, the boundary of glass transition temperature. Okay? Then how about semi-crystalline polymer? Same specific volume as a function of temperature. So we're going to consider this semi-crystalline polymer. Okay? As you recall, semi-crystalline polymers have both crystalline region and amorphous region. Therefore, semi-crystalline polymers exhibit both melting temperature and glass transition temperature. So specific volume changes at two different points. First, at Tg, okay, it increases. And at Tm, at melting temperatures, it shows abrupt increase, like this. Okay, and this melting is first order transition. Okay, that's the main difference between amorphous and semi-crystalline polymers. Okay, as you see from here, glass transition temperature Tg is below Tm. Okay, for semi-crystalline polymers, in general, Tg is located in between 0.5 Tm and 0.8 Tm. Okay. So there are many different ways to define glass transition temperature. In the textbook, they say that below glass transition temperature, there are no or little cooperative segmental mobility of polymer chains, like 10 to hundreds of polymer chains. They do not show any movement below Tg, but above Tg, they show that kind of cooperative segmental mobility. Okay, that's one way to define glass transition. Another definition would be like Tg is the temperature where the polymer chains show like micro Brownian motion. You know what Brownian motion is, right? Okay, so there are many different ways to define, and there are many different characteristics at which the glass transition temperature shows. Okay? Another way to measure or determine glass transition temperature is based on, so basically another way to determine viscoelastic property Tg is by stress strain is experiment. Okay. What you do is very simple. You basically measure the mechanical property of a certain sample. Let's say that we have polymers with this shape. Okay? And you apply tensile stress or tensile strain. Let's say that we apply small tensile strain in this direction. So here tensile means basically elongation. Okay, you just hold the sample and you just stretch it. Okay, if you apply small strain, the length of this sample will change from L0 to L. Okay, and here the strain epsilon is defined as the change of length upon tensile strain over original length. Okay, this is the definition of the strain. Okay, and as you apply small tensile strain, what you do is you measure stress, okay, to maintain strain at L. Okay, this is a simple stress strain experiment. Okay, and stress denoted as sigma. Okay, stress is also basically a kind of pressure. So pressure is force per area, and it is known that stress is proportional to strain with a certain proportionality constant. Okay, so this is stress is proportional to strain, tensile strain, with a proportionality constant E. Here E is called Young's modulus. Okay, it basically tells you about stiffness of the sample. How stiff is the sample? Okay. Okay. Then let's imagine what would happen to this stiffness or Young's modulus of the polymer sample above Tg. Okay, we mentioned that Tg is a kind of temperature, okay, in which polymer chain shows like cooperative segmental mobility or micro-Brownian motion, something like that. So above Tg, polymers somewhat move more freely than below Tg, right? Which means that at a boundary of glass transition temperature, the stiffness or Young's modulus will decrease, right? The polymer sample would be more or less soft compared to below Tg or frozen liquid, right? Okay, so by simply measuring this mechanical property or Young's modulus, we can determine glass transition temperature. Okay. So let's consider two different cases. First, okay. So you apply a certain fixed tensile strain and you measure stress as a function of time. Okay, at time 0. Okay. Since you apply a certain strain, they'll afford a certain amount of stress, right? And let's say that you remove that strain. Okay, what will happen? If the sample is totally elastic, okay, such as like rubber band, okay, if you remove the strain, it totally recovers, right? So stress, if it is totally elastic, okay, when you hold the when you maintain the specific amount of tensile strain, then the stress will be constant. This is totally elastic case. Okay, totally elastic. If it is simply viscous or liquid, fluid, then there will be no stress, right? It becomes totally zero. And since polymers are viscoelastic, it exhibits both solid-like and liquid-like properties. Stress as a function of time shows this kind of behavior. Okay, viscoelastic. Okay. All right. So, as I mentioned, when you check the stiffness or Young's modulus as a function of temperature, you can determine glass transition temperature. So, it is known that if you plot log E, Young's modulus, as a function of temperature for polymer samples, it shows this kind of behavior. Something like this. Okay, like this. For amorphous sample. Okay. So, at very low temperature, it shows like glassy behavior. It's like a frozen solid. And this transition is basically glass transition. And above glass transition temperature is not totally viscous liquid at the beginning. It shows something like rubbery properties. So this part is called rubbery plateau. Okay? And at high temperature becomes melt or viscous liquid. And the like boundary between rubbery plateau and viscous liquid is called rubbery flow. Okay, so this is the behavior of amorphous polymer. How about semi-crystalline polymer? Semi-crystalline polymer also have glass transition temperature, so it shows like this, rubbery plateau, and since semi-crystalline polymers exhibit melting, okay, at melting it decreases abruptly. Okay, so this is semi-crystalline polymer. Okay, it shows both Tg and Tm. Okay. All right. All right. Okay. Then let's see what affects the glass transition temperature of amorphous polymer. There are many factors which affect the Tg value. Okay, we can simply understand that any factors which affect the mechanical properties, as determined in this Young's modulus change as a function of temperature, will affect glass transition temperature, right? Okay, there are many different factors. First, molecular weight. Okay, as the molecular weight increase, Tg will increase, right? It's obvious. Right? Actually, there is a formula which shows this behavior. Tg Tg infinity minus some constant over molecular weight. As the molecular weight increases, Tg increases. Okay. The details will be covered in class. Another factor, crystallinity. If the polymers are more crystalline, it will be more stiff, right? Crystallinity increases, Tg also increases. Okay. Cross-linking. If cross-linking increases, cross-linking density, also Tg will increase. Right? What else? Chemical structure. Okay. If there are functional groups which are more stiff functional group, or if there are more like intermolecular force between chemical groups, intermolecular force, Tg will increase. Okay, so there are many different factors which affect glass transition temperature. Okay, sum up here. Okay, let's briefly summarize the Tg. So Tg is very unique properties of polymers. So Tg is universal with polymers. So basically all polymers exhibit Tg. Amorphous polymers have Tg, and even semi-crystalline polymers, since they have some amorphous regions, they also have Tg. Also, other than polymers, some other amorphous materials, including inorganic materials, also have Tg. So it is the most important single parameters that you first measure when you have a specific polymer samples. That's why we learned how to do the DSC measurement. Okay. Then how can we modify, how can we change glass transition temperature of polymer samples? There are many different ways. The first way is by cross-linking. Okay. Remember this graph, right? The Young's modulus as a function of temperatures. So the amorphous polymers have this kind of behavior. Okay. Glassy, leathery, rubbery, and the liquid. So what happens if you cross-link polymers, cross-link polymer chains? So if you lightly cross-link, for example, if you form like rubber, basically this viscous part disappears and the behavior of this Young's modulus as a function of temperature changes like this. Okay? Basically, over a large range of temperatures, the polymers exhibit like large rubbery plateau. So that's why it is rubber. Similarly, if you heavily cross-link polymer samples, then basically it becomes very like hard, rigid materials, very glassy, hard materials. So the first way to modify glass transition temperature is by cross-linking. Second effect which can affect the modification of Tg is crystallinity. Okay? So if you compare amorphous and semi-crystalline polymers basically have a little bit like larger Tg, and also they have some lower plateau, and after that they have melting temperature like this. Okay, so semi-crystalline polymers have a little bit larger Tg compared to amorphous polymers if you have same polymer backbone. third cause is molecular weight. So you might recall from the molecular weight measurement part that there were many different kinds of molecular weight for polymers, and some of them were related. It's not some of them. One of them was related to the viscoelastic behavior of polymers, which was number average molecular weight. So number average molecular weight affect the glass transition temperature of the polymers. So if you have same kind of polymers with different molecular weight, different number average molecular weight, the glass transition temperature follows this kind of formula. So Tg is equal to Tg infinite. Infinite means Tg of the infinite molecular weight minus some constant K over molecular weight. Which means that if the molecular weight is small, if the polymers have short chains, they have lower glass transition temperature. The reason why is very simple. So we learned that glass transition is related to the cooperative molecular chain motions, right? Then, if you have shorter chain polymers with smaller molecular weight, those polymers with short chains will have more chain ends, right? If you have polymer chains something like this, these ends are called chain ends, and these chain ends act as a packing defect. Okay? There should be some like volumes near this chain end which cannot be used to pack with each other to form like hard glassy state at low temperatures. So short chain polymers, low molecular weight polymers have more chain ends, basically more packing defect, so that's why low molecular weight polymers have lower glass transition temperatures. So for example, for polystyrene with number average molecular weight over 35,000 have basically same Tg of about 100 degrees C. But on the other hand, same polystyrene with molecular weight of 9,000 have like minus 12, which is like 88 degrees C. Tg of 88 degrees C, much lower than the high molecular weight polystyrene. Another way to modify glass transition temperature is plasticization. So remember, when you have first learned about Tg, the first question was, why do you really need to care about Tg? And it was related to the use temperature of the polymers. And one example was about this plasticizer of phthalate. Right? So what exactly is plasticizer? And why adding more plasticizer lowers Tg? So plasticizer is basically the low molecular weight additive which you add when you make polymer samples. Since this is just low molecular weight additive, it will basically act as defect for packing, similarly to the chain ends for low molecular weight polymers. Okay, so for example, if you make PVC, you add some amount of dioctyl phthalate as plasticizer, and if you add more of this plasticizer, the resulting polymers have lower Tg, and their physical properties becomes more flexible, more soft. Right? Another example is the water in chewing gum. So you have experienced chewing gum, right? Gum is basically solid, right? But if you put it inside of your mouth and having like the basically water inside of your mouth, because of those water absorption, water acts as kind of plasticizer inside of this chewing gum. Chewing gum is a kind of polymer, polyvinyl acetate, and this water absorption basically lowers the glass destruction temperature. That's why as you chew gums, it becomes like flexible, soft material. All right. Then let's see some of the effect of chemical structures. How different chemical structures affect glass transition temperature. You guys already have learned about this in terms of melting temperature, right? It's quite similar. So first, for the in terms of change stiffness. So compared to these flexible structures, if you have more like benzene ring, something like this, it becomes more rigid, right? The chains are more stiffer. Then the Tg will increase, right? So if you compare these two polymers, okay, this one is much more flexible than this one. Right? The resulting Tg is 206K for this polymer, 357K for this polymer, right? That's why, the reason why is that this polymer has benzene ring inside of the main backbone. Another effect is polar or secondary bonding effect. Okay. So if you compare these two vinyl polymers, polypropylene and polyvinyl chloride, since PVC have this chloride group, which is polar, which means that there will be more like higher, larger amount of molecular interactions between polymer chain. That's why PVC has higher Tg compared to polypropylene. And in terms of these molecular interactions, compared to van der Waals interaction, hydrogen bonding is larger, the effect of hydrogen bonding. Compared to hydrogen bonding, ionic bonding is much larger. That's obvious, right? And also, chemical cross-linking has much larger effect on glass transition temperature. So let's see another example. If you compare the Tg of polymethyl acrylate, polyacrylic acid, and polyzinc acrylate, this is just polar polymer, which has Tg of 10 degrees C only. Polyacrylic acid can form much higher, like larger molecular interaction because of this more hydrogen bonding between polymer chains. If you look at the chemical structure, there is a OH group, CO group here. So there's more like higher possibility of hydrogen bonding with each other. That's why polyacrylic acid have much higher Tg of 100 degrees C compared to polymethyl acrylate with this chemical structure. Okay. There is no OH group here. Polyzinc acrylate is basically ionic compound, and we already know that ionic compound has much larger chemical interaction, molecular interactions with each other. So that's why polyzinc acrylate has much higher Tg of 400 degrees C. Similarly to the main backbone chain stiffness, if you have more steric or stiff side group, it also increases Tg. So if you compare polypropylene and polystyrene, so here we have benzene ring here. Okay. This benzene ring basically for more stiff like polymer chains and also larger van der Waals interactions. That's why compared to polypropylene, polystyrene have much higher Tg. Similarly, if you have more flexible side groups, it tends to lower Tg. So if you compare PMMA with PEMA, so it has a little bit longer chains, right? There's only 3 atoms, but there are 4 atoms here. So these chains will be a little bit flexible, more flexible than this one. That's why Tg is a little bit lower than Tg of PEMA is a little bit lower than PMMA. Another effect is isomerization. if you compare cis and trans form of polymers, cis form has slightly lower TG. It's similar but slightly. Because cis form has a little bit like more unstable basically structure. So if you, but the difference is not quite large. If you compare polybutadiene or polyisoprene of the cis and trans form, the difference is very small, right? The difference of the TG is very small, okay, 3 degree or like 17 degrees C. All right. Final effect that we can consider is copolymer. What if we have copolymers of two different kinds of monomer? If the copolymer is random copolymer, then you basically have averaged TG values between these two monomers. So for example, if you have random copolymer comprising two different monomer, and the TG of each of those homopolymer is TG1 and TG2, the resulting random copolymer have kind of average TG, and based on this equation, you can calculate the average TG. If you have information about the weight fraction of the kind of mixing ratio, right, between these two different kinds of monomers. If the copolymer is block copolymer, it could have two different TGs, right, or just one TG if the mixing ratio is very small for one kind of polymer. Before we move on to the theory of TG, there's also a very interesting behavior of amorphous polymer, which is called physical aging. It's very important, and also is used in when you use polymers in industry. You remember the graph, the specific volume as a function of temperatures, right? Remember that as you decrease the temperatures from the liquid state, right? At TG, it changes the slope, something like this, right? That's how you measure TG, right? But the thing is, this state is not thermodynamically stable phase. You remember what really TG stands for, right? At higher TG, at higher temperature, higher than TG, the polymer changes. Basically, amorphous polymers are in liquid state. Below TG, they are amorphous but frozen state, frozen glassy state. So this is just frozen, like an ice. It is not thermodynamically stable phase. So if you have some polymer samples below TG, and if you wait for a long time, it slowly relaxes to thermodynamically stable phase, basically theoretical equilibrium, okay, after a long time. So if you store a certain amorphous polymers for a long time, months or years, then those polymers are in this state, not here. Okay? Then, if you have this state of polymers, how can you measure TG by doing DSC measurement? If you recall the basic experiment for DSC measurement, what you have done is something like this. You first heat up the sample, okay, and you cool down the sample, and then again you heat up the samples, right? Remember? That's how you measure DSC for any kind of samples. And the second heating, from the second heating, you basically determine TG or TM. The reason why is there is a physical aging, the relaxation to theoretical equilibrium. Okay, by doing the first heating, you basically make the polymer into liquid state, and you cool down slowly, and it becomes this out of equilibrium glass state here. Okay? Basically, you removed the history of this physical aging for this amorphous polymer, and then you heat it up again. Then you will experience this slope change at Tg, and you can measure glaciation temperature by DSC measurement. Okay, that's why you have done this second heating cycle when you measured DSC for polymeric samples. Okay, so I'll stop here and let's move on to the theory of Tg, how polymer physicists try to explain this glass transition. Okay, now let's start lecture number 9. So, in lecture 8, we have learned about glass transition temperature and how complicated, how ambiguous the behavior of glass transition of amorphous polymer is. So, there have been some efforts to explain why there is glass transition for amorphous materials. So last 50 or maybe more years, many polymer physicists try to solve that question. Why is there glass transition in amorphous polymers or amorphous materials? There isn't still any obvious theory, but there have been some theory which try to explain the glass transition behavior. So I'll briefly introduce a few of them. So as you see in the lecture note, there are a few theories which try to explain glass transition, including free volume theory, kinetic theory, and thermodynamic theory. And the bottom two, kinetic and thermodynamic theory, are quite complicated, so which can be covered in graduate school lectures. So in this lecture, we'll only slightly cover free volume theory, what free volume theory is, and how this theory explains the behavior of glass transition. So we already have learned about free volume when you learned about the chain and the effect on glass transition temperature, right? Chain and act as packing defect, basically making more free volume. Okay? So what exactly is free volume? So if you look at the, let me just enlarge this quite a bit. So cannot really change it. So if you look at the lecture note, the volume of polymers, V, the specific temperature T, comprise two different parts, V0 and Vf. V0 is the volume, VO is the volume occupied by the polymer chains. Okay. On the other hand, this Vf, denoted as free volume, is just empty space between polymeric chains. That's why when you have more the chain ends for small molecular small molecular weight polymer chains, which have lower Tg. Okay, so basically, overall polymeric sample have total volume, which comprise occupied volume and free volume. So this free volume theory explains the behavior of Tg based on this free volume. So this occupied volume changes if the molecular vibration of the polymer chains change as a function of temperature. So if you look at this graph, okay, this is the occupied volume as a function of temperatures. Okay, as you increase the temperature, occupied volume slowly increases. Right? On the other hand, this free volume, free volume is this part. So let me remove this. Okay, so the occupied volume follows this line, and free volume is this region. Okay, so as a boundary of glass transition temperature Tg. Okay? Below Tg, free volume also increases slowly as a function of temperature. Okay? Because of the more molecular motions, like here, like rotational or translational motion of the polymer chains. But above Tg, you remember that above Tg there are more like cooperative polymer chain motions, including like tens of, even hundreds of polymer segmental. Okay? That's why above Tg there are more free volume increase here. Okay? That's why if you plot volume as a function of temperature, okay, there is a slope change for the total volume. Okay? So based on this free volume theory, we simply explain why there is a Tg. Because at a boundary of Tg, the free volume change, the degree of free volume change is different between below Tg and above Tg. Okay, principle, right? So we'll get back to this point later. Okay. Another feature of glass transition temperature is called time temperature superposition. So we already have learned about this before. When you first introduce glass transition temperature, you have learned about the dependence of glass transition on the rate of experiment, or the relative rate of the rate or the speed, the time scale of the experiment. That is basically shown here. Okay, so let's see the graph. So the y-axis is log Young's modulus G modulus, and x-axis is log T time. Okay, and we have learned that as the time scale increases, if you do the experiment in more slow way, okay, then Tg basically decreases, right? So decreased Tg means the mechanical property Young's modulus also decreases, like this. If the time scale is short, like here, if you do the experiment at a faster rate, then you remember the silly putty behavior? The resulting polymers behaves like solid, like the brittle material, right? Which means that the mechanical property, the Young's modulus, increases, something like this. So at a specific temperature, for example at T1, the Young's modulus behaves something like this as a function of time scale T. Okay? And if you change the temperature, for example, like lower than T1 or higher than T2, it basically shows similar behavior. Then we can say that if you have this one curve, which is called master curve, basically showing the time scale dependence of the mechanical property or the glass transition temperature, if you have these one master curve, since the other curve at other temperatures basically shows similar behavior, okay, if you have information about this one master curve, then you can determine the other curves at different temperatures if you have how much like the how much shift occurs as a function of temperatures. Okay, that's called time temperature superposition. Basically means that shorter time scale short time scale high temperature basically gives the same result as you do the experiment at long time scale lower temperature. Okay, so all you need is just one master curve and how much shift you basically get when you change the temperature. Okay, so you can get that information using some equation called Williams-Landau-Ferry or WLF equation. So as I just mentioned, here shows the another variable which is called Deborah number, okay, which explains this time temperature superposition behavior of polymers. Okay. So Deborah number is defined as the ratio between relaxation time and experimental time. Okay. So based on this kind of Deborah number or time temperature superposition, you can understand that high temperature short time scale or low temperature long time scale or room temperature moderate time scale, all of these basically will give us the same result. Okay? They are kind of compensated with each other. Right? So let's try to find this shift factor, how much shift we can get as a function of temperature using this theory, WLF theory. All right, let's begin. So WLF equation looks like this. Log tau at higher temperature, higher than Tg, over tau at Tg. Tau is the kind of time scale, relative time, relaxation time scale, is equal to minus C1 T minus Tg over C2 plus T minus Tg. And here C1 and C2 are some constant. And in this equation, in WLF equation, this C1 and C2 have are kind of universal constant. So they have similar values for different kinds of polymers. And this equation is applied when the temperature is in between Tg and Tg plus 125 degrees C for amorphous polymers. And this time scale, relaxation time scale, is proportional to the viscosity, which can be measured using viscometry. Okay? And this ratio of tau at different temperature, the ratio of viscosity at different temperatures are called shift factor and denoted as A sub T. This is the shift factor that we want to find based on this master curve. So if you have information about master curve and if you have information about this shift factor, if you have information at one temperature, you can predict the behavior at another temperature. So this is just a result, and we want to derive this equation based on free volume theory. So let's do that. So remember that based on free volume theory, total volume is equal to occupied volume plus free volume. Okay. And if you recall physical chemistry class, thermal expansion coefficient can be written this way, right? Especially in liquid phase and also gaseous state. Okay. Thermal expansion coefficient is 1 over volume and derivative of volume over as a function of temperature, right? This is the thermal expansion coefficient in the liquid state. This is the thermal expansion coefficient in glass state. Okay. In glass state, we don't really need to care about free volume, right? But because there is not much change, but in liquid state, there is the change in free volume is much larger, okay, compared to glass state. Okay. All right. So we will use this to variables. And there is another equation which is called Doolittle equation, which is empirical equation that has been found by this scientist named Doolittle. What he did is he measured basically viscosity as a function of the volume. And the Doolittle equation looks like this. Okay. So the Doolittle equation shows that the eta, so this viscosity, is a function of free volume. Okay. It's A times exponential some constant B times V minus Vf over Vf. Okay. So this guy basically did a lot of experiment using paraffin wax and basically changing the temperature, because by changing the temperature he can change the free volume. Okay. And he found out the basically the relation between free volume over the polymer volume and the viscosity. Okay. So using this equation, since this is the empirical equation, let's define a new variable, fractional free volume, basically the fraction of the free volume over total volume. So let's denote fractional free volume as small f, which is Vf over V. Okay. Then this Doolittle equation can be changed in this expression, right? If you can just put f here, right? Then eta is A times exponential B 1 over f minus 1. Okay. Right. Then this fractional free volume f. So let's denote this f as Fg when the temperature is below Tg in glass state, and above Tg, f should be equal to Fg plus thermal expansion coefficient times temperature change, right? Okay. So here we basically assume that this fractional free volume changes linearly as a function of temperature, since we can assume that the free volume also changes linearly as a function of temperature. Okay. So since we get this expression from the Doolittle equation, let's say that we have we measure this eta at two different temperatures, as eta 1 and at eta 2. Okay, and the ratio between these two values, if you just divide one of these two with another eta, then you'll get this expression. Okay? Since both etas have A will disappear, and we'll have this expression. And let's say that this eta 1 was measured when the temperature is above Tg, and this eta 2 is measured at Tg. Okay, then these two ratio here will be same as this, right? F2 is basically the Fg, and F1 is basically this Fg plus alpha times T minus Tg. Okay, and if you take the log, we can remove this exponential. Right? If you rearrange this, what you get is basically this expression, and this is basically WLF equation. Right? Very simple. Right? And if you check this universal constant for some polymers, you can clearly see that for some different kinds of polymers, including polyisobutylene, natural rubber, styrene, etc., the C1 and the C2 constants are quite similar, except with a few exceptions. It's quite similar with each other. Okay. So anyhow, the derivation is not important. Anyhow, the the main point here is that you can determine this shift factor, which will give us the prediction of the behavior of polymers at different temperature based on the master curve. And over this idea, this shift factor was obtained simply from free volume theory, right? Simply assuming that there is a free volume, and free volume changes as a function of temperature, and especially at different degree, based on the boundary of glass transition temperature. Okay, so this is pretty much it for the free volume theory. Right? Okay, let's move on. Okay, let's see a little bit more on glass transition, and also some other aspect of the glass transition. Let's consider elastomer, like a rubber. Okay? Remember that if you plot the Young's modulus, local Young's modulus as a function of temperature, amorphous polymer looks like this behavior. Lightly closed polymer, which is elastomer, basically shows this kind of long range rubbery plateau. And semi-crystalline polymers have this kind of behavior, a little larger Tg, but here basically they show Tm here. Okay. And if you check the effect of this light cross-linking and also the molecular weight, you guys need to first understand what exactly for this kind of like larger range of the rubbery plateau for elastomer. So let's first consider the effect on molecular weight. So this larger range of rubbery plateau means that these polymers, these elastomers, have like the what is it called, the elastic behavior like rubber. Okay? And that elastic behavior is based on cross-linking. Also, if you have like higher molecular weight, and if you have more entanglement, in Korean in ongkim, okay, then it will have more elastic behavior, right? So if you have just some polymer, some amorphous polymer with different molecular weight, then as you increase the molecular weight, you will have a larger range of rubbery plateau. Okay, and also if you increase the degree of cross-linking, then it will also increase the range of rubber plateau, at the same time increasing the height, the position of the rubber plateau. Okay, that's the some aspect we can consider for elastomer and glass transition. And here shows some summary of like different kinds of polymers and their thermal properties and their process and use temperature. So let's see some of them. Let's first consider glassy or amorphous polymers such as polystyrene and PMMA. Okay, and the processing temperature is like at least 50 degrees larger than glass transition temperature, because at this temperature, this polymer can be in the liquid state. Okay, so we basically process them here at higher temperature, and if you want to use these polymers as glassy polymer, like hard materials, you have to use it at least below Tg, right? Because at below Tg here, at below, this is Tg, at below Tg, polymers are basically at in glassy state. But real use temperature is a little lower than that. Okay? If it's too close to Tg, it will have a little bit flexibility like leathery properties. For highly crystalline polymers such as HDPE, high density polyethylene, we process those materials above melting temperature, right? because we need to form a liquid state, and we use these polymers below TM and even lower lower than the melting temperature. Similarly, semi-crystalline polymers also process temperatures above TM and use it between TG and TM, right? Because at this state, basically, the materials are solid state. Okay? For leathery polymer, such as PVC, we process it above like 50 degrees higher than TG, and we use it near TG, right? Because near TG, the polymers are in leathery state, right? For example, if you want to use like auto seat, right, like leather, then the TG of those leathers are near like room temperature. Elastomers, similar process temperatures, and we use it higher than the TG because elastomers are basically in rubber plateau region. Okay? Finally, let's briefly summarize the experimental technique that we can use to measure TG and also TM. Some old method is called dilatometry, which is basically used to measure the volume of the polymer sample. Maybe the Doolittle used this dilatometric method to measure the free volume changes as a function of temperature. So since this is very old technique, it's very tedious and takes a long time. Another old method is indentation. So basically, you measure the mechanical property of the certain sample by like poking with a like sharp like what's called sharp like indentation is something like you have some samples and you just poke it with a some sharp edge as a function of temperature. If this is solid, it will be really hard to like poke it to make a dent. But if it's like flexible, then you can easily make a dent. This is also an old method, but still it is used. Like nano indentation technique is widely used. And DSC is commonly used, as you already have done it in your sophomore years. You basically use reference sample and your own samples. You just do the second heating, like first heating and cooling and second heating. During second heating, you measure the change of the enthalpy, right? And in comparison with the reference sample. Okay. So for example, if you have the, usually you have this kind of data, right? This kind of data. If the polymer sample is semi-crystalline, you have TG and you also have TM. Right? Then how can you determine specific temperature? How can you just denote specific temperature as TG or TM? Okay. For TM, if the peak is sharp, if the enthalpy peak is narrow, you denote TM as the onset point here. On the other hand, if the peak is broad, something like this, you denote it as here, the final TM, final temperature. Similarly, we can also determine TG in two different ways. So for TG here, you basically have different slope like this, like this. Okay. So you can either denote TG as this half point, right, in between, or as the onset here. So yes, this is more commonly used, and you can easily determine the TG and TM of polymeric samples within a very short time. It takes only like tens of minutes. Right? So this is pretty much it on glass transition. So after this, we'll move on to the mechanical properties of the amorphous polymers, and which is related to the glass transition. All right. In this lecture, let's cover the mechanical property of polymers. How we determine it. We briefly covered the viscoelastic property of polymers, and we can determine it, especially TG, based on the mechanical measurement or the tensile strain stress experiment, right? So let's extend that contents a little bit. Okay, remember that polymers exhibit both solid-like and liquid-like behavior, which is called viscoelastic behavior. Okay, so fluid is like viscous and solid is elastic. Okay, and viscous or viscosity eta, okay, is the characteristics of the viscous liquid. Okay, and elastic behavior can be determined by elastic or Young's modulus, which is denoted usually as E or G. Okay, all right. So what's interesting thing about viscoelastic behavior? All right. In this lecture, let's cover the mechanical property of polymers. How we determine it. We briefly covered the viscoelastic property of polymers, and we can determine it, especially TG, based on the mechanical measurement or the tensile strain stress experiment, right? So let's extend that contents a little bit. Okay, remember that polymers exhibit both solid-like and liquid-like behavior, which is called viscoelastic behavior. Okay, so fluid is like viscous and solid is elastic. Okay, and viscous or viscosity eta, okay, is the characteristics of the viscous liquid. Okay, and elastic behavior can be determined by elastic or Young's modulus, which is denoted usually as E or G. Okay, all right. So what's interesting thing about viscoelastic behavior of polymers? Let's look at some videos. Okay, so this video basically shows the viscoelastic effect of polymer samples. There are 3 different properties, which is very interesting. The first one is Varus effect. Second one is Weisenberg effect. The third one is called Kaye effect. Okay, so all of them are quite interesting behavior, which is only shown for polymers or any materials with viscoelastic characteristics. Okay,
All right. So let's cover the mechanical property. So polymers exhibit viscoelasticity. So basically they exhibit both viscous behavior or viscosity and also elastic behavior. Okay? So for example, if it is elastic, you can imagine a rubber. Right? So we can express it using Hooke's law, right? Like a spring. Okay. And remember that the stress is a kind of pressure, okay, which is stress, sigma. So force per area. Okay. And there are two different kinds of stress usually used to determine mechanical property of a certain material. The first one is tensile strain or elongation. Second one is shear strain, shear stress. Okay? If you apply this kind of tensile or shear stress, okay, the sample would exhibit strain, tensile strain or shear strain. Okay, tensile strain, the first one, tensile, is denoted usually as epsilon. It's defined as the change of the length from the original length. Okay, and tensile strain, shear strain are, if you apply shear stress, the sample would be pushed this way, right? Okay, so if you apply shear stress, okay, so there will be some angle, okay, so tangent theta will be considered in dealing with shear strain. Okay, so this is the about the elastic behavior. Okay, how about viscous behavior? Viscous behavior of the fluid can be determined by viscosity, right? And it is known that if you apply a certain stress, the viscous property is related to the rate of strain, not strain itself. If you remember, the stress is proportional to strain for elastic behavior, but stress is proportional to rate of strain, or dE over dt. Okay, and we can say that like epsilon dot or r dot, okay, the rate. Okay, so we need to consider both elastic and viscous behavior of the polymers, since polymers are viscoelastic. Okay. First, elastic behavior. So stress is proportional to strain. Okay, so if you plot stress as a function of strain, it will show relatively linear behavior. Okay, and the slope is given by Young's modulus. Okay, very simple. Okay. How about viscous behavior? Fluid. There are two different kinds of fluid. The first one is called Newtonian fluid, such as like water, and non-Newtonian fluid. Non-Newtonian fluid. You'll learn about the details about this fluid in fluid mechanics class. Anyhow, let's briefly go over. So, Newtonian fluid, for Newtonian fluid, stress is proportional to rate of strain. And proportionality constant is given as viscosity. Okay? So for Newtonian fluid, stress is proportional to rate of strain and shows linear behavior, and the slope is given by viscosity. Okay, but for non-Newtonian fluid, it is not. Okay, stress and rate of strain does not show this linear behavior, somewhat different behavior. There are many different kinds. The first kind is called show this kind of behavior. It's linear, but it shows some y-intercept, which means that we need to apply a certain stress to move this fluid. So this kind of fluid is called Bingham fluid. And second kind shows this kind of behavior. Okay, as the rate increases, as the strain rate increases, stress significantly increases. And this behavior is called shear thickening. Another one is called shows this kind of behavior. Okay, shows denoted as shear thinning, and polymers shows this shear thinning behavior. So if you look at this graph, it shows that as the rate increases, stress increases, but the slope decreases, which means that for shear thinning or polymers, if you plot viscosity is the ratio between stress and rate of strain. As a function of rate of strain, it shows decrease, right? Okay, for polymers. The reason why is very simple. As you increase the rate of strain, before applying strain, polymers will look like this. Okay, but after applying a certain strain, polymers will be somewhat stretched, right? So it shows relatively small viscosity. It can move more freely than before applying a strain. Okay? Alright. So we need to consider both elastic behavior and viscous behavior to describe the behavior of viscoelastic characteristics of polymers. So stress can be expressed as strain this. Okay, and this equation holds only for small deformation. If deformation is too large, polymer sample could be like broken or something like that. So this equation shows the viscoelastic behavior of polymers, and this equation is called constitutive equation. Okay, so we can consider polymers as some kind of spring and some kind of liquid, viscous liquid, fluid. Okay, so we need to model this behavior of polymers. So we can model it by comprising spring and fluid, so which is called mechanical model. So there could be two different kinds. We can locate spring and fluid, which is a kind of dashpot, in series, or we can put them in parallel position. Okay, so this model on the left, which basically locate spring and fluid, in series are called Maxwell model, and the model on the right is called Voigt-Kelvin model. Okay, so let's just consider Maxwell model, and you can just look it up, the Voigt-Kelvin model in the textbook. Okay, all right. So Maxwell model. So there are two different stress. If you divide the stress of elastic behavior and fluid behavior, stress of a spring would follow this equation, and stress of dashpot would be viscosity times this. Okay, and from Maxwell model, the spring and dashpot located in series. Okay, the stress, overall stress, if you apply certain stress to this model, to this object, overall stress will be same as this, right? And overall strain will be the sum of spring strain and dashpot strain, right? Okay. 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 If you take the derivative of the second equation as a function of time, what you get is d epsilon dt is equal to d s dt plus d dt, which should be equal to s dot over e plus d over eta, right? Okay, and which is same as dot. Okay, and since sigma s, sigma d are all same as sigma, what you get is epsilon dot is equal to sigma dot over e plus sigma over eta. Okay, so we have constitutive equation for Maxwell model, or we can say you can rearrange this and we express it in terms of sigma dot e sigma plus e dot. Okay, so for small deformation, if the strain is small, the viscoelasticity basically shows linear behavior. Okay, sorry, this is equal. Okay, okay, so if you apply certain strain, okay, basically shows linear behavior. Okay, above a certain stress, it does not show this linear behavior, something like this. Okay, so below a certain point, it shows linear behavior. Okay, above that is not linear anymore, so that point is called yield point. And above yield point, we say that here shows elastic behavior. Here we say is shows plastic behavior, plastic deformation. Okay. Okay. So we have seen the simple derivation of Maxwell model. You can also check the Voigt-Kelvin model in the textbook. So you can compare the difference between Maxwell and Voigt-Kelvin model. Okay. And okay, today's lecture is on free radical copolymerization.